purpose of this video is an attempt to explain what electricity is and to give you a general overview of how electricity works. We are going to do this by exploring two formulas that are essential for anyone who is in the electrical engineering field. Of course, there are a plethora of other equations that intertwine with each other, but to avoid us getting lost in endless equations, we are going to stick to those two formulas, and hopefully they are sufficient to help us have a better understanding of how electricity works. My name is Farai. I'm a licensed electrician, and welcome to the channel Magetsi 2.0, your channel that is all about everything electrical. Now, let's get right into it. We're going to start by getting into a couple of definitions, and the first term that we're going to define is electricity. What is electricity? Well, electricity is the existence and flow of charge in a conductive material. Charge doesn't flow in materials like plastic or rubber or a dry piece of wood. These are what we call insulators. Charge flows in materials that we call conductors, materials that have a sufficient amount of free electrons. Examples of good conductors of electricity include copper, silver, gold. These are all good conductors of electricity. The copper cables that bring electricity into your home or into your workshop, they are good conductors of electricity. Now, the rate of flow of that charge is what we call current. And current is either direct current, DC, which flows in one direction, or alternating current, AC, which periodically changes direction. The unit for current is amperes or amps, which is abbreviated by uppercase A. Those who deal with small values of current, which we call small current, that is current values that are below 1 amp, they usually talk more in terms of milliamps or even microamps. When you deal with small current, instead of saying 0.003 amps, it makes more sense to say 3 milliamps. When you flick on that light switch, the reason why that light bulb glows is because of current that flows through the light bulb filament. And when you get an electric shock, it is because of current that flows through your body. So, when you get an electric shock, we say current is the culprit. But can current do it alone? There is no current flow without voltage. Current cannot flow where there is no voltage. Current needs voltage to flow because voltage is the pressure that pushes current through a conducting loop or through an electric circuit. So when you get that electric shock, if current is the culprit, then maybe you say voltage is the accomplice, because current and voltage, they do their thing together. So voltage is the pressure from an electric power source that pushes electrons through a conducting loop, enabling them to do work. In an open circuit, there is no flow of current, so voltage and current are not doing any work. A car battery that is not connected to anything is not doing any work. And just the same as with current, voltage, we also talk of direct current voltage or DC voltage and AC voltage. DC voltage remains constant over a period of time, whilst AC voltage alternates. Voltage is measured in volts, abbreviated by capital letter V. For very small values of voltage, typically below 1 volt, we may talk about millivolts, and for values above 1 volt, we simply refer to them in volts. For example, 48 volts or 230 volts. Then when we enter the high voltage space, or HV, we mostly talk about kilovolts or kVs. For example, instead of saying 11,000 volts, we say 11 kV. And instead of saying 132,000 volts, we say 132 kV. From what we've just discussed, if there's no voltage or current in an electric circuit, then there's no capacity to do any work in that electric circuit. So there is no energy. So the definition of electric energy just builds upon the definition of electricity that we discussed earlier on. So let's go over the definition of electricity again. We said electricity is the existence and flow of charge in a conductive material. So then electrical energy is the energy generated by the movement of charge in an electric circuit. So in other words, that movement of charge in that electric circuit results in the generation of electrical energy. Energy is measured in joules and in watt hours, but for most of our discussions we will refer to watt hours. Since energy consumption is usually in the thousands over a 24-hour period, we mostly talk of energy in terms of kilowatt hours. And without energy in an electric circuit, there is no power dissipated, or there is no power that can be dissipated in that circuit. That is because power in an electric circuit depends on the flow of charge, or depends on electrical energy in that circuit. So power is defined as the rate of doing work, and it is measured in joules per second or in watts. For power in an electric circuit, we will focus primarily on watts, which are abbreviated by capital W. In an electric circuit, power is also measured in volt amperes, or VA. For most large electrical equipment found in homes or industries, we mostly refer to their power ratings in terms of kilowatts. For example, a 2 kilowatt space heater or a 7.5 kilowatt motor. Now, we have several formulas and ways for calculating power in an electric circuit, but we're going to focus primarily on the formula that links current and voltage. Now, we have several formulas that we use for calculating power in an electric circuit, but for the purposes of this discussion, we are going to focus primarily on on that formula that links voltage and current in an electric circuit. So the formula that we're going to explore is power is equals to voltage times current, or P is equals to VI, where P is the abbreviation for power, V is the abbreviation for voltage, and I is the abbreviation for current. Notice that these are abbreviations, not units. For voltage, E may be used instead of V to denote a power source, and E should not be mistaken for energy. Also, U is the ISO abbreviation for voltage. So P, or power, can be EI, UI, or VI. One and the same thing. Now, for those who studied physics in high school, you know that E is a shortened form of EMF, which stands from electromotive force. So some of you might want to know, what about U? What does U stand for? Electromotive force. Just kidding. I'm not quite sure about the origins of U, but some other sources that I saw, they say that it's the Germans who fixed U for voltage, and they conveniently found a word that they fixed to U as well, which is Unterschied, or difference, Unterschied or difference. So, I'm not quite sure about this. You can research it, but and if you have a different opinion, just drop it in the comment section. Since power is the rate of doing work, whenever you see or hear the term rate of, you must know that the quantity that comes after of is divided by time. So when you say power is the rate of doing work, we mean power is work divided by time. Please note that we are using the term energy and work done interchangeably. Now, since power is equals to work done divided by time, then energy or work done is equals to power times time. Now that we have discussed these two equations, let's put them to use by way of an example. If you have a water heater in your house that draws 17 amps of current over a 230 volt supply, what is the power rating of the water heater in watts? And if the water heater runs for an average of 4 hours over a 24-hour period, what is the energy consumption for the water heater per day? Now, the answer to that will be something like this. For part A, we get our power rating by simply multiplying voltage and current, which is power is equals to 230 multiplied by 17, and that gives us 3,910 watts or 3.9 kilowatts. For those of you who are familiar with residential installations, you'd know that that's a 4 kilowatt heater over there. Now let's go to part B. For part B, we know that energy or work done is equals to power times time. So on this example, we are going to say energy or work done is equals to 3.9 kilowatts multiplied by 4 hours, which gives us 15.6 kilowatt hours. This is the energy consumed by this heater over a 4-hour period. Now, if you know these type of calculations, then you are able to calculate roughly how much you spend on your water heater each day. If electricity costs, say, 11 cents per kilowatt hour or per unit in your country or in your state, then you can calculate roughly how much you are spending to keep that water heater running each day. By the way, 1 unit of electricity is 1 kilowatt hour of energy. So for our water heater, we are paying 15.6 kilowatt hours times 11 cents per unit, which is about $1.72 each day. Now, this is just a simplified example to help you understand the relationship between voltage, current, power, energy, and time. Now, in the example that we've just done, I deliberately chose water heaters because water heaters are what we call resistive loads. Now, if it was an electric motors fall under the category of inductive loads, and there are more variables that we have to consider if you are working with inductive loads. And we're going to build upon more of those concepts as we progress. But I hope that you managed to pick something from this video. You managed to at least have a better understanding of how electricity works and the relationship between voltage and current, and how that affects power and how that affects electrical energy in an electric circuit. And I hope to catch you in the next video as we continue to build upon these concepts. Don't forget to like and subscribe. Natenda.